guys, welcome to the machine learning playlist. So we saw in our previous video that we have a hypothesis function, that is this line, and we have a cost function. Now according to this cost function, we will have to modify our hypothesis line so that this line slowly tends to match the actual line. Now we are going to achieve that with the help of gradient descent. Let's come to terms of gradient descent. First of all, gradient simply means the differentiation of a function, and for descent we will have to come to this explanation. Now look closely at the cost function, and since our hypothesis is h equals to theta 1 x, and if we plot the cost function here, it will give a paraboloid graph, something like this. Since we are neglecting theta 0 here, we will only go with theta 1. So we will get this paraboloid graph, something like this, which will have a single minimum. And the minimum will be something, let's call it theta m for minimum. So the aim of reducing the cost function is that we will have to make this line come closer to the actual line. So if you actually plot the cost function according to what we have here, you will slowly notice that the cost function starts somewhere above the curve and slowly gets down to the minimum. So when we have a curve here, we are actually trying to use the gradient of this function to descend down this curve, and this is why it's called gradient descent. Let's calculate the gradient of this term and move on with these calculations. So to calculate the gradient of cost function, we have to take partial differentiation, that is del of j theta naught theta 1 with respect to del of theta naught will be 1 by m okay, and again for theta 1 we have del of j theta 0 theta 1 differentiated with del of theta 1 equals to 1 by m. Now you guys can pause this video here and take a moment and actually try to derive these two functions. These are actually important, and we're going to use these two functions to further calculate our gradient descent. So using these terms, using this gradient descent, we will update these parameters. We will update the weight parameters or the coefficient parameters with the help of this equation. So theta naught nu equals to theta naught old minus alpha. Here is the alpha is called the learning factor. Let me write this down for you. Alpha is called. So theta naught new equals to theta naught old minus alpha derivative of j with respect to theta naught, and theta 1 new equals to theta 1 old minus again alpha derivative of j with respect to theta 1. let's actually use these equations and see if if we are heading in the right direction. Let's see where we can make it. Okay, we can actually rub this out. So okay, so for our first update, we'll have to update theta naught. So the derivative of for theta naught would be 1 by m, where m is 4. We have taken 4 examples, so m is 4. Summation of h of I minus y of I. Now h here is our predicted value and y is our actual value. So let's calculate the difference here. Predicted value minus the actual value. For the first example, the predicted value is 1 and the actual value is 2. So predicted minus actual gives minus 1. Let's actually go to the summation term because we are actually summing them up. Again, predicted minus actual, that is minus 2. Similarly, minus 3 and minus 4. That gives us 10. So the derivative for the first term would be minus 10 by 4. And for the update, we're going to take for the update theta naught old was 0 minus alpha. For the learning factor alpha, we normally take a range of values between 0.01 to 0.1. Now it depends on the type of problem that you have. For this problem, we will take the learning factor value of 0.1. So 0 minus 0.1 into the derivative term, that is minus 10 by 4, and we get 0.25. Now to update theta 1, again we'll go through the same process. So theta 1 derivative is 1 by 4. The difference between predicted and actual value, that is minus 1 multiplied with x, where x is 1. So minus 1 into 1, that's minus 1. And minus 2 into 2, that's minus 4. Minus 9 and minus 16. That gives us minus 30 by 4, right? And for theta 1 new equals to theta 1 old, that's 1 minus alpha, that's 0.1 into minus 30 by 4. That's 1 plus 3 by 4, that is 1.75, right? So we have got our updated new theta 1 and theta 0 values. So we'll write them down here. I hope you have taken this down. So theta 1 would be theta 1, the updated new value of theta 1 would be 1.75, and the new value of theta naught would be 0.25. let's write down our hypothesis now. So our hypothesis H equals to 0.25 plus 1.75x. Let's find out our new values of the new predicted values for given x equals to 1, 2, 3 and 4. Similarly, h equals to, that's 1.75 plus 0.25, that's 1. Again 1.75 square plus into 2 plus 0.25, that's 2.5 plus that's 3.5 plus 3.75. Again, first that would be 7 plus this would be 7.25, and this one would be let me calculate this real quick. 5 point. This one will be 5.25, I guess. Let me know if the calculations are correct. But anyway, so this one will be a 5.5. Alright. So these are our new values, the new updated values. Let's plot them around here. This one's a bit too. Yeah. Let's plot them now. So for 1 we have 2. We have got one value exactly right. For 2 we have 3.75. So this is 3. 3.75 would be somewhere around here. For 3 we have 5.5, around somewhere around here, and for 4 we have 7.25, again here. Let's try to plot this. Now as you can see, the new updated line is much closer to the actual line than the previous line was. So you see how this proceeds. You take out the gradient of the error function, the loss function, and you use that gradient to update your parameters. And when you update your parameters, the hypothesis line actually shifts towards the best fit line to fit all the points that are given. So this is the essence of machine learning. This is how you use gradient descent to actually fit through all of your data points. Before we conclude this video, I want to talk a little bit about this learning factor alpha that we have here. So as we saw in that graph before, this is J versus alpha 1, sorry, theta 1, and we will get this nice convex paraboloid curve. So I was talking about the range of the learning factor values that we take. It's usually between 0.01 to 0.1, but it will depend a lot on the type of problem that you have. But usually we don't deviate much from those values, because see, when you have a value of alpha that is very much less, that is way lesser than these standard values, the algorithm takes up too many steps to actually learn and reach the minimum point. So if here's a minimum point, and if you take the learning factor, the value of the learning factor too small, it will take too many steps to get there, and the learning gets really slow. Again, if we take the value of the learning factor more than say 1 or 2, more than the standard convenient values, the algorithm actually starts behaving haywire. So it takes much larger steps than it is supposed to take. So there will come a point when it will try to overshoot the minimum. All right, it will take too large steps that it is supposed to take, and it will actually overshoot the minimum, and it will keep overshooting the minimum. It will never reach. It will never reach the point where it is supposed to be stable and minimum. So yeah, we normally take the value of alpha to be between the range of 0.01 to 0.1. I guess you got the idea of how we use gradient descent to take a line, to take a best fit line that fits perfectly to all the data points that we have. We will continue with multivariate linear regression from the next video. Thank you for watching and have a nice day.